So let me share. Okay, can you see this slide?
Yes, we see.
Okay, yes, on Monday we talked about the living with sand option, and where one of the key questions will the rock travel to the surface, and some criteria, so how it depends on the velocity or flow rate and the diameter of the sand grains. Then we talked about the infrastructure, the living with sand installation, sand monitoring, using the acoustic sensors, or radioactive detectors to define the level of sand in the separators. And then we talked about prediction of sand failure. There are few methods of predicting sand failure. One is the field experience, on-site rock strength measurements, or laboratory measurements, and metaphysical log and core analysis. Field experiments, as it says for its own, using the analog data or previous field wells behavior. There is one testing for the rock strength, Brinell testing, when you create this indentation and measure this, and then calculate based on the pressure and this indentation diameter. Another one is unconfined compressive strength test, which is more popular because it's more related to the drawdown pressures, which we will see in the next. And in this test, it's very well correlated with the porosity of the sample. Here is the uniaxial compressive strength, and how this classified rock. Like if this is the uniaxial strength is 0, it's a quicksand. It means no consolidation. It's just pouring around without any support. And if this is less than 1,000, let's say it's unconsolidated, and we have hard when we have 20 psi, 20,000 psi. When we push this plate on this sample at 20,000 psi, and it's a crushing, then it's a hard rock, which is quite really hard to crash, and it gets excellent core samples. Another test is the thick wall cylinder collapse strength. When you put core sample into this thick wall cylinder, and then push the perforation and see what is the results of the test. So this will help you to identify what will happen in the reservoir when you perforate it. Will it crash or will it stay as a perforation? And it depends on the again rock strength. Sorry. The petrophysical analysis, as we said, the porosity is very close related to the strength, and the higher porosity, the higher the lower the strength, and the porosity itself is linked to related to the sonic travel time. And if we compare it to the thick wall cylinder strength, you can see it's a the reverse relationship, and this allows us, for example, to from the sonic travel time to the log of sonic to identify, recalculate, or estimate the rock strength, of the rock of the samples. So the lower porosity, greater rock strength, and from that we can say that we can link the rock strength to the sonic travel time logs. Relationship between the compressive strength and the incidence of the rock failure was tested as well. This is a kind of study that was done in Exxon, and this showed that the rock fails at the drawdown pressures, which is 1.7 times of the compressive strength, and that's comes from these results when the different samples compressive strength was tested, was plotted against the pressure drop or the drawdown, and the slope is 0.6, which is 1.7 times of the compressive strength. And here you can see the results of this test or study. This is the early results when you start pouring or flowing the oil through this rock sample, and this is the end result when you have this cavity inside the sand sample. Why I'm showing this to you, to realize how this happens in the reservoir as we flow the oil or gas or water through the reservoir. And this is how these cavities are created in the reservoir. Another drawdown related experiment or the estimation was done in HPHT wells on Norwegian sector, and this showed that at no depletion, the critical drawdown, in other words, the drawdown that is below which we should not expect the sand failure or sand production, is 500. Once the reservoir depleted, which means the overburden pressure is now prevailing and dominating over the pore pressure or reservoir pressure because of the depletion, the critical drawdown or the drawdown that below which we should not expect the sand production is now around 200 bar. So that means if as the reservoir depletes, then the sand failure becomes even more possible, and so therefore we have to realize that even if at early stage we don't have any sand production, during the exploration or appraisal wells, drilling and testing. The increase of pressure depletion, increase of the more reservoir pressure declines, then the risk of sand production, sand failure of the reservoir rock is increasing. And it's especially valid when you cut the water, when water starts producing, starts being produced, the connate water, now the fines that are connected, within the zone of connate water becomes mobile, because now connate water is itself becomes mobile, and therefore and also the velocity of the water is higher, so the sand production, sand failure, the failure of the reservoir for the sand is even more exaggerated. Okay, the description of the sand failure should be based on the or predictions should be based on the availability of representative core material. So you have to have very good core, which is possible only with the good sand, good core taking technique and core handling technique. Carrying out the relevant laboratory rock strength measurements like Grinnell or UCS or thick wall testing. These are giving different data, different properties, but they are characterizing the sand and allowing us to make an estimation or evaluation of rock strength and how much this one is vulnerable to the sand failure, sand production. And the also the as the Exxon's test, it is very important the production conditions. What is the rate? What is the flow velocity in the reservoir? And the comprehensive model for the appropriate mode of rock failure. Like in here, you can see in this diagram, you can see the failure mode and the cause of failure. This is the flow far away from the well, and mainly it's the stress between the difference between the overburden pressure and pore pressure or reservoir pressure and applied drawdown. And here we have shear or compressive forces on the sand grain, and by this the sand grains may be detached from the basic material and start to moving inside the reservoir. Drawdown near the wellbore, we have a tensile pressure, so tensile forces when it's just a dragging the sand grains from the sand body, and erosion as it starts as some first of all flow, and then the migrating fines or sand grains are starting to shear and erode the rock itself, and the closer the wellbore, it becomes even harder, and the velocity increases, and therefore the more damage to the more sand failure happens to the near wellbore zone. The cost of sand control is a kind of issue that we have to consider before choosing any sand control methods, because every sand control equipment, sand control measure will create a any sand control equipment will create an obstruction in the wellbore, and first of all, it's high skin, and also it is a extra cost. It's a also obstruction in the well intervention or any other logging PLTs or any logging to identify to define the problems with the well producing zones, etc. Here you can see well productivity measurement during the installation of internal gravel pack. Internal gravel pack is when we gravel pack the perforations, and as you can see, at the perforations state we have a 31 PI, and as we kill the well to do this gravel packing, and then gravel pack, this is getting as low as 4.4 even after the producing half year. So only 14% of the productivity of the well comparing to the just the perforated well is remained. On the next slide, you can see the comparison of the productivity or skins, to be exact, on Chirag wells of ACG, and here you can see that cased and perfed wells with this, which are the red dots, red circles, are very low in comparison with the expanded sand screens, the gravel packs, and the standalone screens. Although some standalone screens are started with the low skin, but then as the time goes by and the sand is plugging the screen, the skin was increasing, and so that's about the sand control cost. When you do this, you have to realize that you may reduce your productivity, but and apply this only if it is justified by the very severe damage from the sand production. So as we reduce the productivity of the of our wells, then we have to drill more wells to develop the field. Of course, it will increase the capital cost per well, because now we add cost for the sand control equipment. May require, again, because the productivity is reduced, early installation of artificial lift, which is again additional cost, and higher abandonment pressure and reduced oil recovery, as we will have to abandon the well at the higher pressures, which are still not able to lift the oil to the surface. Okay, and here you can see the comparison between the internal gravel pack, external gravel pack, and perforated completions, their productivity, number of wells required to reach field development plateau rate, and required gas lift for each cases. These are a kind of general estimation, and it might change from field to field, depending on the what we have in the reservoir, what the reservoir rock properties, etc. So, talking about sand control, there are two main categories of sand control. Arch stabilization, when we try to kind of create within the reservoir some kind of sand bridging or sand arching, so that the to increase the strength, not strength, but resistance of the sand to the flow, to the destruction, fine migration. And under this, we can use the rate control, measuring and testing the wells to identify maximum sand free rate, which means that we should not produce at the higher rates than this maximum sand free rate, because sand will be uncontrollable, and for that we have to limit the drawdown so that the stress on the reservoir rock is reduced, and we have to be very careful with the high water cut and high GOR wells, because again high velocity of water and water wet rocks, as well as when we have high GOR wells and near wellbore, when you have free gas, it will be even at due to the high velocity of gas, we will have some problems with the sand detachment from the sand body, rock body, even at higher rates. Non-impairing completion techniques, again reducing flow velocity at sand face, which is the horizontal wells, multilateral wells, deviated wells, when we have a long contact with the reservoir and drawdown is lower, and the flow velocity is the reduced due to this long contact. Selective perforations, selecting only strong intervals. Oriented perforations, when we perforate the in orientations in the maximum stress directions. So we have we perforate the in a stronger distribution of the stress, and perforation density, phasing, and interhole diameter should be taken into account in this selective perforating methods. And chemical consolidation, when we inject some gravel, consolidated gravel or chemicals to consolidate the with the resin coating the sands around the near wellbore, and that makes this the very weak sands to be consolidated and to prevent the rock failure. The next one is mechanical exclusion, when we put some equipment or installations on the sand face or downhole completion as a consolidated gravel filling perforations, screens, standalone screens, the consolidated gravel filling perforations and wellbore, pre-packed screen, premium screens, expandable screens, gravel packing, and frac packing. These are, as you can see, listed in order to of increasing effectiveness and reliability. So gravel packing and frac packing are the best ones. We will talk about these methods individually, but before talking about this, let's have a look in the some critiques about different sand prevention methods. So chemical consolidation may provide some permeability reduction, placement and reliability issues, like it's a injection of the chemicals and how it will react, how it will be placed, in which areas it will be, zones it will be placed, is again the issue, a concern. It might be effective for only short intervals. Screens, slotted liners, special filters, again, lack of zonal isolation, high workover and placement works, longevity of devices. So the longer device, the difficulty to put into the wellbore, plugging and screen collapse, when the this will again decrease the permeability or conductivity between the wellbore and the reservoir. And if we have damaged it during installation, then it is just a waste of money. So these are I'm not going to go through each one. The gravel packing, again, PI reduction, as we saw. All of them have a kind of negative effect of placement and workover difficulties, complexity. Again, if we do the frac pack and we may have propant flow back, or so there's no propant in these wells, so there's no pressure, sand control. Selective perforating also have a reduced inflow area, because we now change the phasing of the perforation to 100 degrees. So only in two directions perforations we reduce the inflow area and create artificially tortuous way or passes for the flow into the wellbore. The same with oriented perforating. Production rate control. If you allow some sand, then it is erosion of facilities, potential for lost production. As you limit your production, sand monitoring may be issue, and of course separation and disposal issues at the surface are costly and environmentally it may be an issue and concern again. Okay, so let's talk about now, after considering these critiques, how we can exclude the sand. Again, one strategy is to achieve sand exclusion by filtering produced solids before they enter the wellbore, which is screens and gravel pack, as I said. And another strategy is reduce the flow velocity by the rate control, or designing high-angle, horizontal, multilateral, or hydraulically fractured wells, in which the flow velocity will be reduced. So and that will reduce the risk of high velocity fluid hydro-down pressure stress on the rock, and it will reduce in its turn the risk of sand failure. Sand exclusion, mechanical sand exclusion methods, including, as we said, standalone screens, open hole gravel pack, cased hole gravel pack, or high rate water packs, cased hole frac pack, selective or oriented perforations, expandable sand screens. These are kind of having a different area of different kind of conditions to be applied. For example, open hole gravel pack can be used in very dirty or poorly sorted sands at high rate wells with large reserves when you want to produce at very high rates, and but the gravel pack is very sensitive to shale production, the reactive shales, when the shale becomes swelling and starts migrating, and these shale fines may fill in the gravel and reduce the permeability of the gravel. So that's kind of the downside of the gravel packs. So let's start one by one, talking about each of them. So the standalone screens are just the slotted liners. They have a machined on pipe slots at the very small slots, and these slots are usually made in a size that should be, the size of these slots should be equivalent to the, well, not equivalent, but smaller than the grain size of the sand. Another type is the wire rapid screens, when we have wire welded wire providing the sand control, and pre-packed screen, and woven metal mesh and expanding screens. The slotted pipe for sand control is, as I said, just a pipe with the holes on it, and these slots are preventing sand going into the wellbore. Wire rapid screens are the screens that are the slotted are created by this wrapping the wire, and the distance between this wire or the allowance between this wire wrapping again is controlling the sand production. Therefore, we have to choose this type of wires based on our sand properties, sand specifications in terms of grain size, in terms of mesh size, etc. These are the pre-packed screen. When we have two screens and the gravel pack or the sand pack between these two screens, and these screens are holding this gravel pack in place, and this gravel pack provides most sand control. And this is the example of this. And then meshed woven mesh and expandable screen. When we have this mesh type of the sand control, and this is the expandable sand screen when it expands just against the reservoir when we want to. So sand control by slotted screen alone standalone screens. This is a mechanical, low-cost sand control option which stops sand movement into the wellbore. Of course, it will work well with large drained, very well sorted sands because it has no kind of diversion or flexibility in the sand grain size. So if we have poor sorted grain sizes, like grain sand with different grain sizes, then the smaller grains will go through this screen, or even worse, it might plug these holes, and this also it is very vulnerable against the shale sands, because shale may plug these screens. And the another issue is that it works better if the larger grain size bridging on the face of screen, and then this grain size, these bridges are creating additional sand control, not allowing, and this also requires some stable drawdown in the wellbore to provide the more stable production conditions at the downhole. So it was brought in from the water wells, the wells that were producing water for irrigation or usage, where those wells are shallow, uniform sand, but the oil and gas is produced from the much deeper, and when the heterogeneity and the grain sizes are different, so it requires a special approach. Not in all wells or reservoirs it may work, and in horizontal wells we may use these as there is a lower drawdowns, and the other one is pre-pack. In horizontal wells, pre-packed screens are more popular. Wire rapid screen, as I said, it is we have a base pipes here, or it might be base slotted base pipe like here, and the wire is wrapped around these rods or base pipe, and these wires are providing the sand control. The configuration or form of these wires are conical to allow the sand, to provide sand plugging these pathway, so that if the sand enters or sand goes through this pathway, then it wouldn't plug here, and it wouldn't create additional obstruction on the flow path. You can see the tolerance gap between the wires is 2 thousandths inch, so it might be very small tolerance, small kind of, it is a tolerance, it's not a size. The common size, gap size between the wires may be 12 thousandths or 8 thousandths for different gravels, for different sands. Pre-packed screens are similar to wire-wrapped, but here we have 2 screens. One is wire-wrapped and another one is the 2 wire-wrapped screens, and between them the gravel pack, which provides the most sand control. Of course, the first one, in inner screen, is keeping the gravel to flow from the moving of this gravel, and the outer also plays a role of sand control and also keeping this gravel pack in place. But main sand control is done by the gravel pack inside between these 2 screens. Okay, pre-packed screens can be prone to plugging, especially if there is a shaly sand. Equivalent inflow area for pre-packed screen can be less than 5% of whole flow area, and premium screens or simple wire-wrap screens have now largely replaced by pre-packed screens because these are providing better sand control. So this is a cut view of the pre-packed screen. Metal woven mesh or premium sand screens are even more sophisticated in terms of we have a different mesh size, different size of mesh put on each other, and these are providing the sand control for the starting for the different size of the sand grains, and these support layers like this base pipe is providing the mechanical strength to stand against the flow, and typical flow area is about 30%, and it is thinner than pre-packed screens because of course these meshes are very thin relative to the pre-packed screens, and premium screens are preferable for sand control in compacting reservoirs or harsh installation environments, long horizontal open hole wells. So these are used for those wells because these are more. These can be put into these horizontal wells or multilateral wells, and it works better. These are different metal woven mesh sand screens. Again, the cutoff view, several mesh size with the starting with the larger and ending with the smaller. Another one is expandable screens. It is expanding it is more applicable for the medium rate oil wells, like up to the 15,000 barrels of fluid. Not effective for gas production because of erosion of these meshes, and powerful in soft formation when you have a and it can be installed. It can kind of stand against these formations and still provide good sand control. It has a good burst strength, but relatively low collapse strength. Also, screen plugging concern. Of course, the plugging is the concern for all screen types, because all sand control types, because we have a small sized holes to be for flow, and when any small diameter grain sizes are inserting into these holes or the pathways, it will be plugged naturally, and the effectiveness of this, the productivity will be downgraded, and it might be in some cases very substantial. Therefore, we have to be careful with the even the choosing the correct sand control methods based on these reservoir rock properties, reservoir rock characteristics. And one of the failures that standalone screen is, for example, or any screen is very vulnerable, is the erosion or plugging in, and even mud cake debris may be plugging the screen itself. So if it is put on the open hole, and we have to be careful with the choosing mud fluids and the chemicals that we apply, especially in horizontal wells, where even if we clean this mud fluid from the top, the bottom of this will be still plugged in. It's valid, of course, for the horizontal wells. So that's it for today. Sorry for a long talk. Is there any questions? Hello? Are you with me?
Yes, we are
Hello? Here. Okay. Any questions?
I don't have any question.
Okay. So if no questions, have a good time. I will be here at 3. If any questions from the FTP groups. Okay. Thanks for your attention and participation. See you next week. Again, I will try to find a way to share individually your quiz results, and as soon as I find this way, I will share them. Okay? Have a good time.
Sağ olun müəllim.
Sağ olun.